Okay, welcome everyone to the Astronomical Society of Edinburgh. This is our mid-month meeting. We tend to have 2 meetings a month. And this is what's coming up tonight. I'll have a few introductory slides about what's coming up soon. And then we'll have our main talk tonight from Whitham over in Alaska. So thank you very much for joining us from there, Whitham. Or Whit, as you call it. We have a few new members this month, David Buxton and Ria Urban. So I don't know if any of them are here, but can we welcome our new members in the usual way? And welcome to all visitors as well, wherever you are in the world. We usually get people from all over. And if you want to join our society, the fees are very modest at £30 or £15 for concession. At this time of year, it's wise to join us after the 1st of April because you get a much longer membership as well. If you want to stay in touch with us, these are all the usual ways you could find out what's going on with us: our website, Facebook, Twitter, and all the videos of our meetings are on our YouTube channel afterwards, so you can see a large number of those from the last few years on there, and there's been some amazing talks on there. This is what we've got coming up over the next couple of months. On the 1st of April, we're doing something slightly different for our members. So it is a members' night. It is for members only at the Augustine United Church in Edinburgh, and it will be on Zoom as well. If you're in Edinburgh, then you are welcome to drop in and join us for that meeting, but it won't be on YouTube at that time. So we'll have a number of short presentations for members, plus we'll be getting out quite a few of our old antique telescopes that we have lying around in cupboards doing nothing at the moment, so that should be interesting. On the 6th of April, again for members only, we have our imaging and observing group, and at that Des Loughnane is going to be telling us about observing eclipsing binary stars. The 15th of April, creating miniature stars and astrophysical phenomena with giant lasers from Dr. Kate Lancaster. The 6th of May is Weird New Worlds from Dr. Beth Biller. On the 20th of May, we have Emily Lagawala on exploring 25 years of Martian discoveries. And on the 17th of June, we have Volcanoes of the Solar System from Dr. Natalie Starkey. And we'll be filling in the 2 meetings every month slots as well. So lots to look forward to. And Nigel and his team are doing amazing work booking people for these talks, including tonight's talk. So that's the introductory stuff. So that's it from me. Over to Whit in Alaska. So thank you.
Okay, thanks, Mark. And thank you for inviting me to do this talk. Let's see, you should be able to see my full screen now.
Yeah, we've got that.
Right?
Thank you. Yeah, it's great. Thank you.
Okay, good. My name is Whitham Reeve. I'm from Anchorage. I was born here in Anchorage. And I'm going to be talking about meteor trail reflections in the high frequency radio band. And these were reflections that I observed in Anchorage in 2020. It took me about a year to process the data. So I actually prepared this talk in 2021. And so what I'm going to talk about is who I am, what I do, some fun facts, or maybe more realistically, estimates of meteors, the concepts between meteor trail reflection, some considerations that I had to take into account to do the observations in the high frequency band, a little bit about my instrumentation, and then we'll get into the observations, which are the real heart of this talk. Kids, you can do this at home. My observatories are relatively simple, and I'll be talking specifically about the high frequency radio band, but there are other radio bands that you can use as well, and I'll try to mention those as we go through this talk. Like I said, I've been in Alaska all my life, got my education here, college degrees, and I ran a telecommunications and radio engineering firm since 1975. Now, I don't do engineering anymore. I haven't for over a decade now. But what I do now is I manufacture instrumentation for radio astronomy, and that keeps me pretty busy. But it's not something that's a full-time job. So I have a lot of time to do observations. One of the things that I've been doing recently, or last couple of years, is consulting work for University of Alaska Fairbanks Geophysical Institute with the High Frequency Active Auroral Research Program, or HARP. Some of you may have heard of HARP. It's a huge transmission facility in Alaska that's used for ionospheric research. And one of the things that I've done is establish 3 radio observatories in Alaska, and these are not government funded, these are privately funded. And this shows a map of Alaska. Here's where I am, here where the red dot is, and that's a radio observatory that I started building in 2008. And then in 2015, I built one about 100 and some kilometers southwest of Anchorage. And then a couple of years ago, I got involved with the HARP program up in Gakona, Alaska, and was able to establish kind of an observatory within an observatory up at that facility. So most of what I do is solar radio observations. I also do some Jupiter radio observations. I'm mainly interested in radio science, radio propagation from really low frequencies up into the HF, or high frequency radio band. And I also do the Meteor Trail and Aurora radio reflections at HF. And I use the time frequency stations that are based in the USA. I also do geomagnetic stuff with the SAM-3 magnetometer. So I have that established here in Anchorage as well. So let's get down to business and talk about some Meteor Fun Facts. And really, these are estimates more than anything. But there's a huge, huge number of tiny meteors that enter the atmosphere each day. And these are dust grains that are left over from asteroid and comets as they wander through the solar system. Now, their mass is real tiny, 1/10 millionth of a gram, up to about 1/10 of a gram. And those are the ones that are causing meteor trails that reflect radio waves. And those are the observations that I make. Now, there's thought to be about an equal mass distribution of each particle size. So what that means is there's 10 times more meteors of 1/100th of a gram than there are of 1/10 of a gram. And their diameter, these are small, 2 micrometers or 2 millionths of a meter. And the largest are in the neighborhood of 2 millimeters. Now, over on the right-hand side, you can see a photograph of what would be called a meteorite. And this was recovered in Antarctica, and it's only 60 micrometers wide from end to end. And so I'm not sure how they recovered that, but it turns out that Antarctica is a good place to find meteorites. Now, if all meteorites were this size here, you could put 300 million of them in a soup can. So they're real tiny, but they do leave a trail that reflects radio waves. Now, their speed range, when they come into the Earth's atmosphere, varies from maybe 11 to 72 kilometers per second. And that's determined, those velocities are determined by the escape velocities of Earth, of an object near Earth and an object near the sun. So they vary over a range, and but they're still pretty fast. And I'll have a little bit more about to say about this later. And there's an estimate of 100 to 1,000 tons that enter the atmosphere each day, and about 5,000 tons fall to Earth each year. So the very large majority of these objects, as they enter Earth's atmosphere, totally vaporize, and whatever particles are left over, those are floating around in the atmosphere, and some actually make it to the ground. And so this picture over here on the right is an example of one of those. Now let's talk a little bit about the concepts. When the meteor comes into the atmosphere, it collides with air atoms and molecules in the atmosphere. They have a high velocity and a lot of kinetic energy, and that's converted to heat. The heat vaporizes the surface atoms of the little stone or piece of dust or whatever it is, and this is called ablation. And it turns out that these atoms, these ablated atoms, are ionized. And what that means is that electrons are stripped from the atom or the molecule and are floating around in the vicinity of the object itself. Now, this forms long, thin trails or columns of positive ions and free electrons. And typically these are 50 kilometers long. Now, it turns out that the positive ions, in other words, the nucleus, the basic molecule, or the basic atom, they're quite heavy compared to the free electrons. The free electrons readily interact with radio waves. So, and that's where we get the radio reflections, is from these clouds of electrons. The positive ions don't have a whole lot of effect on radio waves, so we don't see those. The trail itself has got a paraboloid shape, kind of like shown with this sketch in the lower right-hand corner. The altitude range of these meteors when they burn up is in the neighborhood of 85 to 105 kilometers. And if you're familiar with radio, high frequency radio propagation, that is the altitude of the E region of the ionosphere. And it's just a coincidence that that's where they actually get burned up. So the way that we detect these reflections is we have some kind of a transmitter that's broadcasting. The radio waves will go up into the E region or the ionosphere, and they are reflected off of this meteor trail, this trail of electrons that's left by the burned up meteor. And that's reflected then down to a receiver. And this is a form of a passive bistatic radar. And bistatic means that the transmitter and receiver are located at different places. Now, the geometry of this transmission and reception path has to be just so. This drawing that I'm showing you is a two-dimensional drawing, but it's really a three-dimensional geometric problem. And this path could be tilted, but what is required is that the transmitter, the meteor trail, and the receiver all have to be in the same plane, and the incident and reflection angles are equal. And then if we satisfy those geometric conditions, then we will receive meteor trail reflections. Now, I mentioned that this is a bistatic radar. In my case, the transmitter and receivers are separated by a very long distance in the neighborhood of 4,000 kilometers. And I use the WWV and WWVH radio stations that are in the USA. WWV is a time frequency station in Colorado, and WWVH is a identical station in Hawaii. And both of these are quite some distance away. So that means that the radio waves that travel to the reflection point or the trail, meteor trail, have to go quite a ways and then be reflected down into Anchorage. And to me, that's quite a challenging propagation problem. But I'll show you some observations later that proves that it can be done. Now, let me just back up to this. I use WWV and WWVH. Over on your side of the world, there are transmitting stations that you can use that will work probably even better because you don't have the long distance propagation problem like I have. So you, if you have the appropriate receiver, then there are a lot of people in Britain that are actually doing this kind of work right now. So from a map perspective, here's me. I'm up in Alaska, and here's a transmitter down in Hawaii and another transmitter over here in Colorado. And I believe that the reflection region is an oval-shaped region shown in yellow on this drawing. And I really don't know for sure. It could be north, could be farther south, east or west of what I'm showing here. But this is what I think the geometry works out to be. Notice that one station is almost due south, and the other station is almost due east of my receiver station. Now, the problem that I've got is that my transmitter, this broadcast transmitter down in Colorado or in Hawaii, is such a long distance away that the radio waves need to propagate all the way to somewhere near me before they can even be reflected. And so I'm showing a drawing here that shows the transmitter some distance away and a multi-mode or a multi-hop radio path for the HF radio waves. Now, when these high-frequency radio waves enter the ionosphere, they're refracted and go down and will be reflected from the Earth surface, go back up. And this, in order to get to me, I think they have to go through at least 3 hops and maybe 4 or even 5 hops just to get to me. And so I came up with this concept of a virtual transmitter that one of these reflection points, whether it's on the surface of the Earth or in the ionosphere, is the actual radio waves that impinge on these meteor trails, and then reflected down to my receiver that's shown over on the far right of this drawing. So what is required for this to work is that, first of all, there needs to be a path all the way from the transmitter, 4,000 kilometers distance, into my area up around Alaska somewhere, and then they're reflected from there down to my receiver. So the propagation problem is probably a bigger problem than anything for me to receive these reflections in the high frequency band. Now, if you have a transmitter that's close to you, then you don't have to worry so much about that propagation problem. You might have a transmitter that's located a few hundred kilometers away that beams up and reflects off of the meteor trails and then directly down to your receiver. So you're not worried about the big long geographic path that like I do. So the angles of these various paths are going to depend on the number of hops and the distances and so on. So it's I'll stress again that for me, receiving high frequency meteor trail reflections is really a propagation problem more than it is anything else. Now, one of the things that's known and that I've noticed in my own observations is that there are daily, seasonal, yearly, and long-term variations. For example, the daily variations, if we look at the Earth from above the North Pole, let's say, the Earth's orbit is going to be going down, as shown here. And as it moves through the solar system along the ecliptic, then these any kind of dust or comet debris or whatever is going to be swept up by Earth's gravity on the morning side of the Earth. So, and I've noticed this is that particularly in the morning, I see a lot of activity, and I very seldom see activity in the evening. And this could be, part of this is certainly the meteors being swept up in the morning, but it's also a propagation issue for me as well. And then there's also the seasonal variations that in the fall, Earth is tilted, or at least my side of the Earth is tilted toward its orbital path. And in the spring, it's tilted away. So in the fall, I would receive more meteor trail reflections than I would in the spring. There's also some other issues that come in when you're doing the high frequency band or working in the high frequency band, and that's that the propagation conditions vary with the solar cycle, and that's the sunspot cycle. When the sun is active, propagation in the HF band normally is better than when the solar activity is low. And right now we're in a minimum of the solar cycle number 25. It just started here a couple of years ago and won't peak for maybe three or so more years. You also have propagation that's affected by the solar terminator, and that's the gray line that moves over Earth as the Earth rotates and the sun moves overhead. I'm going to talk just briefly about instrumentation. This is a block diagram of what I've got set up here in Anchorage. And the most important pieces of this whole drawing here are the receivers shown in the middle and the antenna shown over on the far left side. Now I use multi-couplers, which means that I can connect up to 8 receivers to a single antenna. And that way I can monitor different frequencies at the same time. I run these through an audio mixer, an analog audio mixer shown here on the right. And then from there, I go to the sound card on a PC. And I run specific software called Argo that gives me a display of the audio that's coming from these receivers. Now, there's a lot of other things that are shown here, kind of infrastructure type things, local area network, the wide area network, or the internet connection. I use time servers to give me extremely accurate timestamps on all my data. Of course, I have power supplies for the electronics and things like that. Now, if you're going to do this at home, you don't need an elaborate setup like this. This could be an FM receiver, and this could be a regular old everyday FM antenna. So in fact, there's a lot of people that do that. And so you don't need to worry about having an elaborate setup shown like that shown here. This is a picture of the antenna that I use. This is called a log periodic dipole array. There's individual elements. These, the longest elements are in the neighborhood of about 3 meters. And it's about 13 meters above ground level on a tower that I built. And it's rotatable, so I can point it in different directions. The receivers that I use are a general coverage receiver. The R75 is very, very popular receiver. It's out of production now. And I'm replacing my R75s with a wideband receiver, the R8600. Both of these are made by ICOM. Of course, you don't have to use ICOM. You could use, if you're a ham radio operator, you could use the receiver in your ham radio transmitter, in your ham radio transceiver. So that's part of my setup. There's other things like the audio mixer and the receiver multi-coupler. There's DC power supplies, time servers, uninterruptible power systems, the LAN and WAN. And of course, the PC is an extremely important part of this. I use exclusively Lenovo PCs. The hardware has extremely good reliability. I run Windows 10 now on everything, and that's not quite as reliable as the hardware, as we all know. Now, the software that I use is called Argo, and this is an older program originally designed for low-speed digital CW or continuous wave type transmissions. And I've kind of adapted it for meteor trail reflections, and it gives you a lot of information. Along the bottom scale here is time. So time moves from left to right. And then on the right hand, you'll see a scale here that's labeled in frequency. And what you're seeing here, when I have my receivers hooked up to this, to the sound card and this software, is that the frequency that I'm receiving is near 15 megahertz, but I'm actually looking at the demodulated signal on this trace here. So you'll see kind of a diffuse trace in the middle, and that's the demodulated signal coming in to the receiver. But then you'll see these blips, and those are the meteor trail reflections. And there's real short ones, and there's also some longer ones shown here. And like just about everywhere in the world, you're always going to have extraneous signals wandering through your receiver passband. So you'll see these like these slanted lines shown here. They'll wander through occasionally, and I don't know the source of those, but they're easy to differentiate between the spurious signals and the actual meteor trail reflections. And I'll show you some more of this here in just a second. So the observations, when I listen to the receivers, the demodulated audio with like headphones or on a speaker, I hear these 1 second or less bursts of tone. And I have my receivers tuned in such a way that the tone that I hear is at 1000 hertz. So I hear these bursts of tones. There'll be tone enhancements. There'll be a stream of these, and they'll have different Doppler frequency shifts. And because of that, the tones that I hear when there are active meteor trail reflections, it sounds like a bell or maybe multiple bells ringing or like a wind chime. And it's actually quite musical to listen to these things. The detection time and rates for me, usually between 4 a.m. and 9 a.m. local time. Now, I'm very seldom up at 4 o'clock in the morning, but I let my receivers run 24 hours a day, 7 days a week. And the Argo software is logging the data for that same period of time. But when I go through and review the data, I find that usually they don't start any earlier than 4 o'clock local time. And I usually don't see them very often any later than 9 o'clock in the morning local time. So these are generally before sunrise at Anchorage that when I have the most detections. And if you go back and look at this drawing of Earth as it's moving in its orbit around the sun, 4 to 9 o'clock in the morning is this region right here, which is the optimum region for, or the optimum time for receiving the meteor trail reflections. Now, sometimes I'll see detections outside that time frame. Some of these may be anomalous. In other words, they may not be meteor trails, maybe something else. But there's no hard and fast rule that says, okay, you're never going to receive anything like this at any other time. So you don't have to worry about that. Now, reflection events, I've in my data for 2020, I recognized them during all months, but not every day of each month. So, and I attribute that to the propagation problem more than there not being any meteor trails, because there are meteor trails just about all the time. Now, I found that I only had a few records in January and October, or I'm sorry, in June, I only had a few records, but in January and October, I had many records. And the October is the fall time. So that kind of stands to reason. Why January had many records, I don't know. That's not an optimum time, but that's what my data showed. Now, the propagation window for me is about 3 hours. So that just turns out it's a characteristic of HF propagation, my location with respect to the transmitters, and that kind of a thing. Now, there's two stations that I monitor. They transmit on exactly the same frequency. So I'm not able to differentiate between them. The signals are very weak, but almost all of my 2020 data was made at 15 megahertz. And I have one image that I'll show later that was at 25 megahertz. And I know that was from the station in Colorado, because only Colorado station transmits on 25 megahertz. The station in Hawaii does not transmit on that frequency. Generally, I need to have a direct path to my receiver in Anchorage from the transmitter in order to see reflections. So that's kind of a propagation problem, or a given of propagation, that I need to receive the signal before I'll see reflections of those signals. Now, the meteors are moving with respect to Earth, or with respect to the transmitter and receiver, so that this introduces a Doppler frequency shift. And these are usually in the range of maybe 5 to 10 hertz. They're not a huge frequency shift, but sometimes I'll see where the reflections will go off scale. But my Argo setup, my software setup, limits the display and the data to within 20 hertz of the center frequency, which is 15 megahertz. And I often see that the Doppler frequency shifts are biased toward negative Doppler shifts. And I can't explain that, but all my data shows that I see more negative Doppler than I see positive Doppler. That may infer something about the meteor radiant, where it's coming from, but I don't really know. Now, there's two kinds of echoes that I see. These are short, the ones I see most of are short duration. They're just blips on the data that I gather on the images of the Argo screen. And these last only a fraction to maybe a few seconds at most. I see streams of these that last up to 2 hours. And this image here shows an hour and 46 minute stream of short duration video, short duration echoes. You can see all these blips down here, and those are all meteor trail reflections. Now, I also see long duration echoes, and these have invariably have horizontal features like stripes or striations. And these last longer than a fraction of a minute, usually a minute, maybe 2 minutes. And the longest I think I've seen is the one shown here, which is 7 minutes. So this is a meteor trail reflection or an echo from a meteor trail that reflected radio waves for as long as 7 minutes. And one of the things about those long duration echoes is that I see these striations. Now, the reason for these striations, you can see these stripes, is that I don't know for sure, but some possibilities are that there's maybe high altitude wind shear. It's known that there are high altitude winds, quite strong, that could cause this. There might be interference between different parts of the meteor trail so that reflections from one part of the trail interfere with reflections from another part of the trail, and so that it causes these striations. There may be multiple trails produced by a meteor group. In other words, it might be a meteor that is flying in formation with other meteors. There may be meteor fragmentation, and that produces these striations. So there's a lot of reasons for that, and but I haven't been able to nail down one or another. Now here's an observation at 15 megahertz, and this is a 12-minute record of meteor trail reflections. You can see this horizontal line in the middle. Now, that's what I call the direct path. This would be from the transmitter to my receiver and not reflected. And then you see these blips. And then also you see a long duration echo here with striations. And so that would be the reflected, the radio wave going up into the ionosphere where the meteor trails are, and then being reflected back down to my receiver. So I'm receiving both reflections and what I call the direct path here in the middle. And this is the frequency over here on the frequency scale on the right-hand side. And you can see that the center frequency that I have set here is 1,000 hertz. That's demodulated audio frequency. and that this particular long duration echo here that lasted, say, 3 minutes, maybe 3.5 minutes, it had up to a 10 hertz Doppler frequency shift to it. So that's a long duration echo. Here's a short duration, another short duration. This slanted line that you see coming through on the left-hand side is a spurious signal from somewhere. Who knows? Here's two 12-minute images that I've spliced together. So this is a 24-minute long stream of short duration echoes, all of these little blips that you see along the line. Those are the short duration echoes, and you can see here's a nice long duration echo that lasts in the neighborhood of maybe 3 minutes or 4 minutes. And you also see some striations over here on the left-hand side that last under a minute, and those are some long duration echoes as well. So this, again, this was made at 15 megahertz, and the demodulated audio or the detected audio in the middle is 1,000 hertz. Here's another nice 12-minute record. This was in January, early January of 2020. And you can see several long duration. Here's some nice striations here. This one lasted maybe a minute, a little over a minute. Here's another one. There's also some short duration blips that you can see here. So this one shows a good example, I think, of both long and short duration. Here are primarily long duration echoes. This was on the 14th of January in 2020. And you can see that this one here it's hard to tell, but it's possible that these three may be related in some way. Maybe there was a group of meteors flying in formation, and as they burned up, they produced these reflections that you can see here. There's also quite a few short duration. Over here on the far right-hand side, you can see a blip. Over here on the left-hand side, you can see some blips as well. Those are the short duration echoes. So there's, according to my text that I have down here, there's at least 7 striations in this long duration echo here. And again, I don't know the source of those. I can make a guess, but I really don't know about what that's about. And another thing to notice about this is that almost all of the echoes that you're seeing have a negative Doppler frequency shift. So the Doppler is favored. A negative Doppler is being favored, and I see that in almost all my records. And again, I can't explain that, but maybe that has something to do with where the meteors are actually coming from. Now here's this one shows 6 12-minute images that are spliced together. And so that's 1 hour and 13 minutes total from left to right. And what I've done is I've stretched this image vertically to kind of enhance the Doppler shown by the reflections. And so you can see there's a lot of reflections. If you look at this and stare at it for a while, you will say, okay, it looks like maybe there's a positive bias on the Doppler frequency that you're seeing here. And this is one of the few records where I see more positive Doppler frequency shift than negative. The white stripe in the middle is what I call the direct path. So that would be unreflected. And but you can see this is just a steady stream lasting an hour and 13 minutes of short duration echoes. There's no, well, yeah, there are some long duration echoes in here, a few of those. And you can see this slanted line coming down just left of middle. And that's, again, that's a spurious signal, some kind of a signal that drifted through the receiver passband. So that would be called interference, but it doesn't detract from the detection of the echoes themselves. Now here's a nice long duration echo or meteor trail reflection. This one lasted a full 7 minutes. I think I showed this earlier, but notice that we have an abrupt start of the echo right here. And that kind of looks like what is called a head echo. And that is not so much an echo as it is not so much an echo from ionized ionized atoms and molecules, but it's a kind of a ball of flame that causes an abrupt reflection that's shown there. And then you can see these striations, and there's quite a few of them, some of them in the positive Doppler range, but almost all of them in the negative Doppler range. That's a nice long duration echo. Now, this is the only record that I have of a 25 megahertz echo. In this case, I have two receivers running, one at 25 megahertz and the other at 15 megahertz. And this upper stripe that you see here is a spurious signal. So we can just safely ignore that. But you can see that I was receiving 15 megahertz quite well, indicated by this line at 1,000 hertz. That's the demodulated audio frequency. And I had my 25 megahertz receiver tuned so that it would demodulate at 990 hertz. So you can see that at 25 megahertz, there's several short duration echoes and a nice long duration echo on the right, but there's nothing happening at 15 megahertz at all. And the likely explanation for that is that the radio propagation at 15 megahertz, the geometry was not correct for me to receive meteor echoes at 15 megahertz, but the geometry was correct at 25 megahertz so that I could receive the echoes that are shown here in this record. So that's the only one that I have at 25 megahertz. That was on 21 December of 2020. And I think, if I remember correctly, I had just set up the receiver like maybe a couple days before at 25 megahertz and got it tuned up and running on my Argo chart. And then I received this nice echo from it. So what's to conclude from all of this? Well, from my perspective, one of the most important thing is that, yes, I can receive meteor trail reflections at Anchorage, Alaska, using the high frequency radio band and the time frequency stations WWV and WWVH. So from a propagation perspective, that's pretty interesting. And being able to receive meteor trails is kind of like a bonus. Now, the demodulated audio, if I listen to it through the speaker of the receiver or headphones. I hear short tone bursts, tone enhancements, bell sounds, and wind chime sounds. Those are the short duration echoes. The long duration echoes are more like bursts of a wavering tone. And I only hear those if the Doppler shift is more than a few hertz. It's pretty hard to hear a 2 hertz beat note. So if it's more than a few hertz, then I can hear this wavering tone. It's actually a musical sound. Now, I received or observed Doppler shifts of up to 10 hertz, but the overall limitation was with the way I had my software set up. So I couldn't see more than 20 anyway, but most of the shifts that I saw were in the neighborhood of 10 hertz. The Doppler shifts that I see usually favored one polarity, usually negative, a few, sometimes positive, but the Doppler most often was negative. The echoes were quite strong, 10 to 20 decibels, and that means that the powers were 10 to 100 times higher than the background noise level. So the echoes that I was receiving were quite strong. I would see these between 4 o'clock in the morning and 9 o'clock in the morning local time, which is, if you look at the way the Earth floats through the solar system, those are optimum times to receive meteor trail reflections. The short duration echo streams that I saw could last up to 2 hours. If I saw long duration echoes, I saw some that were at least 7 minutes long. So that's quite a long time period for a cloud of electrons to stay in position long enough for them to be to reflect radio waves. So I've provided some web links here. You probably can't use those as is. So what I'm going to do is I'm going to put these 2 links right here into the chat, and and then that way you can download these 2 papers that I wrote. One is a really extensive, it's probably 30-some pages long, that describes these meteor trail reflections that I observed in 2020. In other words, the other one here is just a very short 2-page paper that talks very briefly about these. So if you're interested in pursuing this in more detail, I'll put those in the chat here in just a second. So that's pretty much what I have for meteor trail reflections, and I'll be glad to take questions if you have them.
That's great. Thank you very much for that talk. It's really fascinating. And before we go to questions, can we thank Rich for his talk, please?
Thank you. Let me copy these links, and I'll put them in the chat so you can download them.
That's great. Thank you.
Okay, so that should do that.
We got those. Thank you. Yeah. Ian, have you got any questions? Well, I've got a question first of all before we move to the other ones. So you detected these meteors. You've gathered the data. What's the next stage in the analysis? Do you try and tie them up with the visual observations? I mean, what comes next after this?
Okay. Yeah, that's a good question. Now, I don't. Because of light pollution, I can't even see the aurora from Anchorage anymore, not like the old days. So there's really not anywhere that I can go beyond what I'm doing right here. Now, there are some people that have tried to correlate visual observations of meteors with the radio, but you're almost looking at two different types of things. The visible meteors, they may or may not cause radio reflections, and more often than not, probably. So I think it would be really interesting that if somebody could do that, but I'm not aware of anybody that's been really that successful, doing that kind of a correlation.
Okay, thank you. Ian, do you want to see if there's any questions on Zoom for us, please?
Yes, there are, but a couple of questions I'd like to ask. First of all, you mentioned that you see mainly negative Doppler events. Do other stations located elsewhere see positive ones?
On the Doppler, you're referring to the Doppler shift?
Yes.
Yes, that again, that's a great question, and the ones I've only seen a few other people that are using the type of software that I use, and there's been no systematic bias in what I've seen from other people. And so as far as I know, I'm the only one that's doing this in the high frequency band. So it would be, I'm not sure that I could do a correlation with people that are doing it in, say, the VHF band with FM stations or television stations. So I guess I'm not real sure. I think that would be interesting to do, but I don't know of anybody that's done such a comprehensive study like I did. So if there's somebody out there that has, I would love for them to get in touch with me and we could compare our observations.
Thank you. My other question, that presumably it gets quite busy during the regular annual meteor showers.
Okay, yeah, I think that most of the meteor trail reflections that I saw were random. I don't do counting. I don't count the number of reflections that I have like a lot of other observers do. So I can't, going back and I went back and I looked in my data. I tried to correlate them with the various meteor showers. And I didn't see that the correlation was all that great. So I think that what I'm seeing are really the random, which are really the preponderance of meteors that enter Earth's atmosphere are random instead of the showers themselves. So I don't see in my data a lot of correlation between meteor showers and what I've observed. Part of that may be the propagation problem that I mentioned earlier.
Okay. Carol has a question. Does Carol want to ask it?
Thanks very much for your talk. It was excellent. Thank you. Just wondering, what is the HF band? You're primarily working at 15 megahertz because of the transmitters are at that frequency. What is the band?
Okay, the high frequency band covers from 3 to 30 megahertz.
Okay.
And then above that, 30 to 300 is the very high frequency band or VHF band. So all of my observations in 2020 were at 15 megahertz. So that's roughly in the middle of the HF band. Now I have actually 3 receivers dedicated to this, and I'm monitoring 15, 20, and 25 megahertz 24 hours a day, 7 days a week. So I'm at I guess you'd say the upper half of the HF band.
You're at the obsessive end of things, I think. I think maybe that's what people call it. If you have three receivers, that's a lot.
Yeah, I really built it up. Now, I first installed this system for meteor trail observations in 2014. And it took me until 2019 to figure out just exactly what I was seeing. And most of the problem was I was doing it in the high frequency band. Everybody else was doing it in the very high frequency band, and their reflections didn't look the same as mine. So I wasn't convinced for 5 years that I was actually receiving meteor trails. And it wasn't until in 2019, one of my colleagues sent me a professional paper that had some spectra in it, some images of spectra that were identical to the spectra that I was seeing on my Argo plots. And so that was kind of a voila moment for me, is okay, now I know what I'm looking at. And so, yeah, it's been a long, it took a long time for me to figure it out.
Your persistence has paid off. Thank you very much. Thank you. Bye-bye.
Yeah, you're welcome. Thank you.
Ron has a question as well.
Hello, Ron here. Thank you. Very, very interesting talk. If I understand correctly, you're detecting the frequency change. When the frequency changes, you're demodulating into audio to make a sound difference when the frequency changes from 15 megahertz. Is that correct?
Yes, that's exactly correct.
Right. And the transmitters that you're receiving, what are they sending out? Are they just sending out a constant carrier signal, or what?
Yeah, they're sending out a constant carrier that also is modulated with various voice announcements and tones that identify the time. So because of the tuning of my receivers and the very narrow passband of the Argo software, I don't see any of those intentional modulations. I'm only seeing the carrier. And so it's the carrier that's being Doppler shifted. And that's actually what I'm observing.
Okay, that's what I was thinking about. Thank you very much.
Yeah, that's a good question. And that's really a common question. Is it's kind of hard to understand just exactly what you're looking at. But yes, you are correct.
Fantastic. Thank you.
Yeah, you're welcome.
And the last one is from Jonathan. Does Jonathan want to ask?
Yes, thank you. I was just really saying that this negative Doppler that you see, that's the same as a redshift as we'd see in astronomy. Is that correct?
Yeah, I always have to sit and think about that one.
Because it goes to longer wavelengths. So that's
the negative Doppler shift in the radio, it would be the object or the reflection point is moving away from you.
Right. Yeah, that was what I was thinking with
that. So that gives you the negative Doppler shift, is the object is moving away.
Yeah. And so then is because you're predominantly negative, is that because the winds at that altitude are predominantly in a direction taking things away from you? Could that explain it?
No, that could very well be. We do know that there are strong winds at 100-kilometer altitudes, but I don't know if anybody knows the directions of those winds above Anchorage, for example. So,
yeah.
But yes, that could very well be what's going on.
Right. Thank you.
Can I ask one more, please?
Sorry, carry on.
Hi, Andrew Mackey here. Thanks very much for a presentation that could have been complicated, but was made remarkably clear. So well done. You answered my questions by answering other questions in relation to matching the signals you receive to anything identifiable, as in like the Leonids or whatever. But thanks very much. I have to say that personal record for me, when I was about 10 years old, my father and I would listen to shortwave and thought we were doing well to get the weather forecast from Gander and Newfoundland. But Anchorage is just something else. So anyway, well done. Thanks a lot.
Okay, yeah, thank you.
We have a couple of quick questions on YouTube. Have you got time for that? Yeah. Okay. One on the Doppler shift again. Could the negative Doppler shifted reflection be caused by upward lighting ionization discharges known as sprites seen from orbit that can occur as high up as 95 kilometers in the atmosphere?
Yeah, I really don't know if that would be the case, but yes, it could be.
Right. Okay. And one last one here. Can you somehow detect the composition of the meteor analyzing the reflection wavelength of the tail?
Not that I know of. Yeah, you're talking. We have the reflections are from the electrons. So and one electron is the same as another. So I'm not sure that you'd be able to differentiate the composition of the ions themselves, because those aren't what's actually causing the reflection.
Okay, right. Yeah, good. Thank you. Okay, I think that's all the questions. So can we thank Whit again for his talk? That's excellent. Thank you.
Okay, well, thank you. And I'll unshare now so you can have the screen back.
Okay, thank you. That's the end of our meeting tonight. Thanks very much, Whit, for doing that. And hopefully we'll see you all again at one of our future talks. Keep an eye on our website.